There's a hidden layer of the universe you've never seen, a ghostly glow stretching across the cosmos, invisible to our eyes but pulsing with secrets. Picture this: at every direction we look, space is filled with a faint whisper of infrared light, a cosmic echo from the dawn of time itself. This is the cosmic infrared background, or SIB, and it's one of the most tantalizing puzzles in modern astronomy. Think of it like the universe's oldest fingerprint, smudged across the sky, holding clues to everything from the birth of galaxies to the elusive nature of dark matter. But here's the thing: scientists have only just begun to decode its mysteries, and what they've found so far is utterly mind-bending. Imagine standing in a pitch-black room with only the faintest glow of a distant candle. That's how the CIB appears to us, a delicate shimmer against the void, a signal so subtle it took decades of technological advancement just to detect it. Yet within that fragile light lies the story of our cosmos's wild youth, a time when galaxies were crashing together, stars were igniting in fury, and the very fabric of space was still stitching itself into shape. This isn't just ancient history, it's the foundation of everything we see today, and the deeper we dig, the more questions arise. Why does this infrared glow flicker in ways we can't explain? What hidden structures lurk within it? Could it even point us toward the invisible grip of dark matter? That's why we're diving into the 25 greatest mysteries of the cosmic infrared background, a journey through the universe's best-kept secrets. From colossal galaxies hidden in plain sight to the eerie influence of forces we can't yet name, each discovery peels back another layer of the cosmic onion. By the end, you'll see the night sky differently, not just as a static canvas of stars, but as a dynamic, whispering archive of the universe's most dramatic chapters. So let's begin where all great stories do, in the dark with the faintest glimmer of light and the questions it leaves burning in the void. The first great mystery of the cosmic infrared background lies in its eerie uniformity, a haze so perfectly spread across the heavens that it defies easy explanation. Unlike the sharp pinpricks of starlight or the fiery bursts of newborn galaxies, this glow blankets the cosmos like fog, untethered to any visible source. Scientists first assumed it came from the earliest stars, those colossal, short-lived giants called population 3 stars, which theorists believe lit up the universe's dark ages with their furious energy. But here's the catch: when telescopes like Spitzer and Herschel scanned the sky, their data told a stranger story. The glow didn't match the expected fingerprints of those primordial stars. Instead, it flickered with inconsistencies, patches too bright, too dim, or clustered in ways that shouldn't exist if ancient starlight alone were responsible. Then came another tantalizing possibility. Maybe the haze wasn't from stars at all, but from something even more exotic, like decaying dark matter particles. Their faint infrared whispers the only trace of their existence. Imagine the universe's hidden scaffolding slowly unraveling into light, a process so subtle it's taken billions of years to detect. Yet even this theory stumbles when faced with the data. Some regions of the CIB show unexplained clumping, as if entire galaxies, or something even stranger, are lurking just beyond our observational reach, their light stretched and smeared by time into this ghostly canvas. The biggest clue might lie in the conflicting observations themselves. Spitzer, with its keen infrared eye, saw a smooth sea of light, while Herschel's longer wavelength vision caught ripples beneath the surface, like hearing two versions of the same song, each missing instruments the other could hear. This dissonance hints at a cosmic orchestra playing in the dark, its instruments still unknown. Could it be superheated dust from galaxies colliding in the early universe, or perhaps the collective glow of countless black holes, their voracious appetites heating surrounding gas to infrared brilliance? Every answer raises new questions, painting a picture of a young cosmos far more chaotic and crowded than we ever imagined. What makes this mystery so thrilling is its scale. The CIB isn't just a relic, it's a living archive, a snapshot of the universe during its most formative era. Decoding its diffuse light means unraveling the very conditions that birthed galaxies, stars, and the structures we see today. And until we can peer even deeper past the veil of time itself, this universal haze remains one of astronomy's most tantalizing riddles. But if the cosmic infrared background's eerie uniformity baffles scientists, its fluctuations are downright unnerving. Peel back the haze and you'll find patches of light that flicker and pulse with no clear rhyme or reason, like a cosmic Morse code we can't decipher. These aren't random noise, they're structured, clustered, too deliberate to dismiss as static from the universe's infancy. The strangest part, the math says they shouldn't exist. Take NASA's Cyber mission, a rocket-borne experiment designed to measure these infrared variations with razor precision. Researchers expected the fluctuations to smooth out at smaller scales, fading into the background like distant city lights blurring at the horizon. Instead, Cyber found hotspots, pockets of infrared brightness clumped together in ways that defied every model. It was as if someone had scattered handfuls of glowing embers across the cosmic dark, leaving no trace of what lit them. One leading theory points to supermassive black holes in the early universe, their voracious feeding frenzies heating surrounding dust to infrared brilliance. Imagine entire galaxies anchored by these invisible monsters, their violent growth spewing radiation like lighthouses in a primordial fog. Yet even this dramatic explanation falls short. The fluctuations are too widespread, too smeared across time and space to pin solely on black holes. Then there's the shadowy possibility of protoclusters, vast, unseen gatherings of galaxies in the universe's first billion years, their collective starlight stretched and dimmed by cosmic expansion into these infrared whispers. Picture a bustling metropolis viewed through frosted glass. You sense the movement, the density, but the details blur into a ghostly glow. Yet when astronomers train their best telescopes on these patches, they catch nothing. No visible galaxies, no obvious sources, just the maddening flicker of something hiding. Could the answer lie beyond physics as we know it? Some theorists whisper about primordial magnetic fields woven into the fabric of space itself, twisting the infrared glow into these strange patterns. Others wonder if we're seeing the echoes of cosmic strings, hypothetical flaws in space-time left over from the Big Bang, vibrating like guitar strings and shimmering with infrared energy. What's certain is this: the fluctuations are a breadcrumb trail leading deeper into the cosmic unknown. Every failed explanation forces us to rethink the universe's early years, not as a stately march toward order, but as a riot of chaos, collisions, and forces we've yet to name. Until we solve this puzzle, the cosmic infrared background remains a mirror held up to our ignorance, reflecting back not just light, but all the questions we still can't answer. Now we arrive at one of the cosmic infrared background's most perplexing gaps, the case of the vanishing galaxies. Theoretical models paint a vivid picture of the early universe, a rampaging nursery of newborn stars, their furious energy heating surrounding dust until it glows like embers in the infrared. The math predicts countless galaxies should be blazing in this light, their combined output matching the CIB's diffuse glow. But when astronomers point their most powerful telescopes toward these predicted hotspots, they find emptiness. Where are all these missing galaxies? The discrepancy isn't slight, it's colossal. Some estimates suggest we're seeing less than half the infrared sources our models say should exist. It's like hearing a roaring crowd through a closed door, only to open it and find a handful of murmuring voices. Could our instruments simply be missing the faintest galaxies, their light stretched beyond recognition by cosmic expansion? Deep field surveys from telescopes like Hubble and James Webb push further each year, uncovering previously invisible galaxies lurking at the edge of detection. Yet even these revelations barely dent the deficit. There's a stubborn mismatch between what should shine and what we can see. This opens the door to wilder possibilities. What if gravity itself behaved differently in the early universe? Modified gravity theories, like MND, suggest the rules we take for granted might warp under extreme conditions, altering how matter clumped together in those primordial epochs. Perhaps galaxies formed in ways our current physics can't predict, their infrared signatures scattered or suppressed by processes we've yet to imagine. Then there's the dark matter angle. If dark particles interacted more strongly in the past, they might have sculpted invisible structures, vast halos cradling fledgling galaxies, their dust glowing in infrared but their stars too sparse to spot. Imagine a cosmic puppet show where the strings remain unseen, while the puppets cast shadows just beyond our view. The most tantalizing clue comes from stacking, a technique where astronomers layer countless faint images, teasing out signals buried in noise. When applied to the CIB's darkest patches, stacking sometimes reveals something not galaxies as we know them, but smudges of light with no clear shape or origin. These ghostly traces hint at galaxies so ancient their starlight has been stretched into near oblivion. Yet even these detections barely account for the missing glow. What's at stake isn't just a census of early galaxies, but our understanding of cosmic evolution itself. If the models are wrong, we might be missing entire chapters of the universe's story, epochs where matter behaved in ways that defy textbooks. And if the galaxies are there, hiding in plain sight, their elusiveness suggests a universe far stranger, far more inventive than we ever dreamed. Until we solve this riddle, the CIB remains a celestial detective story with the best clues still hidden. The spectrum of the cosmic infrared background should be a cosmic fingerprint, a neat, predictable pattern telling us exactly which engines powered its glow. But when astronomers finally mapped its light across different wavelengths, the data refused to cooperate. Instead of a smooth curve matching known stellar or galactic emissions, the CIB's spectral shape bristled with kinks and bumps like a radio dial stuck between stations. This wasn't just noise. These anomalies suggested entire populations of objects or phenomena we've yet to catalogue, shining in ways that defy the laws of thermal physics as we understand them. One glaring inconsistency centers on the mid-infrared range, where the CIB's brightness spikes unexpectedly. If this were merely starlight reprocessed by dust, the usual suspect, the spectrum should taper gently at these wavelengths. Instead, it flares sharply, as if something out there is generating heat at temperatures too extreme for ordinary star-forming regions. Enter the rogue hypothesis. This excess could be the death rattle of dark matter particles. Certain theoretical models suggest these elusive particles might decay into photons, releasing energy precisely in this problematic infrared band. Picture an invisible cosmic scaffold slowly unraveling into light, its decay imprinting this spectral hiccup across the sky. Yet even this elegant idea struggles to explain why the anomalies cluster unevenly, flickering brighter in some patches of space than others. Then there's the black hole contender specifically, the universe's first quasars. These behemoths, fueled by supermassive black holes at the hearts of young galaxies, would have gorged on surrounding gas, spewing radiation that could twist the CIB spectrum into these strange shapes. Simulations show their accretion disks might have burned hotter and dirtier than modern quasars, shrouded in thick dust that reprocessed their fury into infrared excess. But when astronomers scour deep field images for these primordial monsters, their numbers don't add up. Too few quasars, too much anomalous light, another mismatch leaving scientists scratching their heads. Perhaps the most tantalizing clue lies in the spectrum's dip at far infrared wavelengths, a deficit of light where models predict a surplus. This could hint at something freezing cold lurking in the early universe, vast reservoirs of molecular hydrogen or icy dust grains, absorbing and re-emitting the background radiation in ways that carve this spectral pothole. Alternatively, it might reflect a cosmic epoch when star formation briefly stalled, leaving a cold fingerprint in the infrared record. The spectral anomalies force us to confront an uncomfortable truth. Our playbook for cosmic evolution might be missing entire chapters. Whether it's dark matter's ghostly decays, black holes behaving badly, or physics beyond the standard model, the CIB's light refuses to fit into tidy boxes. And until we crack its spectral code, these wrinkles in the data will keep whispering of a universe far weirder than we ever imagined. One of the most electrifying possibilities about the cosmic infrared background is that it might be carrying messages from the most elusive substance in existence, dark matter. For decades, this invisible cosmic scaffolding has teased astronomers, revealing its presence only through gravity's pull on galaxies and clusters. But what if the CIB's ghostly glow is the first tangible signal of dark matter's hidden nature? The idea hinges on a thrilling premise. Dark matter particles might not be completely dark after all. If they occasionally decay or annihilate one another, the energy released could manifest as faint infrared photons woven into the CIB's tapestry like secret ink. Picture trillions of these particles drifting through space, occasionally colliding and dissolving into bursts of light. Each annihilation too subtle to detect alone, but collectively painting the infrared sky. Theorists call this the decay channel, and certain dark matter candidates like sterile neutrinos or weakly interacting massive particles WIMP could leave exactly this kind of fingerprint. The math is seductive. Some models predict the CIB's unexplained fluctuations align eerily well with the expected signals from dark matter annihilation in the early universe. It's like finding a faint cosmic Morse code that matches a language we've been trying to decipher for a century. But not everyone's convinced. Skeptics point out that the same infrared anomalies could stem from mundane astrophysics, superheated dust in primordial galaxies, or the collective glow of countless black holes. After all, the early universe was a riot of extreme phenomena, many of which we're still cataloging. The debate crystallizes around a single question: is the CIB's light too smooth to be dark matter? If particles were decaying uniformly across space, the glow should be evenly distributed, yet the CIB flickers with unexplained clumps. Proponents counter that dark matter wasn't perfectly spread either. It pooled in halos around galaxies, potentially creating those very fluctuations. The most tantalizing data comes from cross-referencing the CIB with gamma-ray maps. If dark matter truly decays into infrared light, it might also produce gamma rays in specific energy ranges. Intriguingly, some gamma-ray excesses, like those detected from the Milky Way's center, align roughly with the CIB's anomalies, as if both are fragments of the same puzzle. But correlation isn't proof, and alternative explanations like pulsars or cosmic rays muddy the waters. For now, the CIB remains a cosmic Rorschach test. Some see dark matter's signature written boldly across it, while others insist we're misreading ordinary astrophysics. Either way, this mystery forces us to sharpen our questions. Future telescopes, like the Nancy Grace Roman Space Telescope, could settle the debate by detecting individual infrared sources currently lost in the haze. Until then, the possibility lingers. We might already be staring at dark matter's first visible tremor, hidden in plain sight. The deepest shock about the cosmic infrared background isn't just what it contains, but when it appears. Recent observations have ripped up the cosmic rulebook, revealing infrared light flickering in eras so early that stars shouldn't have existed yet. This is the too early signal, a paradox that's sending shockwaves through cosmology. Picture the universe's first chapters, a dark, featureless void after the Big Bang, where matter hadn't yet clumped into stars or galaxies. Conventional wisdom says this epoch, called the Cosmic Dark Ages, should be just that dark. Yet when telescopes like Spitzer and Hubble peered back toward these primordial times, they caught whispers of infrared light where none should be. It's like finding footprints in bedrock from an age before anything could walk. Then came JWST, With its unprecedented infrared sensitivity, the telescope aimed at galaxies from the universe's first few 100 million years, and the data was even more confounding. Not only did these ancient galaxies appear shockingly bright in infrared, but their collective glow hinted at something even older lurking behind them. Simulations suggest these early stars needed at least 200 million years to form and heat surrounding dust enough to emit infrared light. But JWST observations suggest the process happened twice as fast, as if the young universe skipped steps in its own evolution. Some galaxies appear mature far sooner than physics allows, their infrared signatures implying they'd already lived, died, and polluted space with heavy elements before they supposedly had time to exist. This forces a brutal reckoning with our cosmic timelines. One radical explanation: the first stars weren't the lumbering giants we assumed. Instead, they might have been smaller, hotter, and more frenetic, igniting in pockets of dense gas that collapsed faster than models predict. Imagine a wildfire spreading through dry grass compared to a slow-burning log. These dark stars, theoretically fueled by dark matter annihilation rather than nuclear fusion, could have flared up violently and vanished, leaving behind an infrared afterglow that stains the early universe. Another possibility is even more unsettling. Our understanding of cosmic expansion is fundamentally flawed. If the universe expanded slower than we think, early galaxies would have had more time to evolve, their light redshifted into the infrared we see today. But this contradicts decades of precise measurements from the cosmic microwave background. Alternatively, there might have been exotic energy sources at play, primordial black holes evaporating, or phase transitions in the fabric of spacetime itself releasing bursts of heat. The implications are staggering. If stars and galaxies formed earlier than possible under current physics, we might need to rewrite the laws governing how matter behaves under extreme density and temperature. Or worse, we could be missing entire phenomena that jump-started cosmic evolution, processes so alien they don't fit any existing framework. JWST next deep field observations might settle the debate, but for now, the too early signal remains a glaring crack in our cosmic origin story, one that hints at forces we've yet to name. Here's an eerie cosmic coincidence that's kept physicists awake at night: the uncanny echoes between the cosmic infrared background and the oldest light in the universe, the cosmic microwave background. On the surface, these two phenomena shouldn't speak the same language. The CMB is the afterglow of the Big Bang, a snapshot of the universe just 380,000 years old, while the CIB is a murky fossil of stars and galaxies forming hundreds of millions of years later. Yet when researchers compared their maps, they found strange harmonies, subtle patterns in the CMB's polarization that seemed to ripple in sync with the infrared glow. It's like finding two clocks from different centuries ticking in perfect unison. The most puzzling alignment centers on something called B-mode polarization, twists in the CMB's light thought to be carved by gravitational waves from the universe's violent birth. These primordial ripples should be random, a chaotic fingerprint of spacetime's earliest tremors. But in regions where the CIB glows brighter, certain B-mode patterns appear slightly more pronounced, as if something in the infant universe left a mark that persisted across cosmic epochs. The odds of this happening by chance, less than 1 in 10,000. One radical explanation: the same force that sculpted the CMB's polarization also imprinted the CIB's structure, an unknown field or particle that bridged these vastly different eras. Picture a cosmic pendulum swinging through time, nudging matter into alignment long before stars ignited. Some theorists propose early dark energy, a fleeting form of repulsive gravity that flared up in the universe's first second, then vanished. If it existed, its shockwaves could have shaped both the CMB's polarization and the distribution of matter that later became the CIB. Then there's the skeptic's take: maybe we're seeing galactic dust's dirty fingerprints. The Milky Way's own interstellar particles can polarize light in ways that mimic primordial signals, and if these dust clouds overlap with CB observations, they might create false correlations. Yet meticulous filtering by experiments like Planck and Bicep/Keck has scrubbed most local contaminants, and the alignment persists. The stakes couldn't be higher. If this link is real, it suggests the universe's first moments and its adolescent years were entangled by forces beyond our current physics. We might be staring at evidence of a cosmic domino effect, where the Big Bang's aftershocks dictated where and how galaxies would light up billions of years later. Or more unsettlingly, we could be glimpsing a flaw in how we measure cosmic light itself, revealing blind spots in our most trusted tools. Either way, this ghostly synchronicity between the CIB and CMB is a riddle wrapped in the universe's oldest light. Dust might seem like a cosmic afterthought, fine particles floating between stars, barely worth a glance. But in the hunt to decode the cosmic infrared background, it's become the ultimate trickster, muddying the waters with false leads and phantom signals. Here's the problem: interstellar dust doesn't just sit there. It absorbs starlight, heats up, and re-emits that energy in the infrared, mimicking the very exotic phenomena scientists are desperate to isolate. Imagine trying to hear a whisper in a windstorm. That's the challenge dust creates when we stare into the CIB's enigmatic glow. Take the case of anomalous microwave emission, a mysterious signal once thought to be evidence of spinning nanoparticles or even dark matter decay. For years, it pulsed across surveys, sparking theories until researchers realized it was just warm dust, vibrating at frequencies that masqueraded as something far more exotic. This kind of cosmic camouflage isn't rare. Dust grains come in endless varieties, some crystalline, some fluffy, others laced with complex hydrocarbons, and each type emits infrared light in subtly different ways. When you're dealing with the faint, diffuse signal of the CIB, these variations can twist data into shapes that look revolutionary until the dust settles, literally. Enter SOFIA, the Stratospheric Observatory for Infrared Astronomy, a telescope mounted on a modified jetliner to soar above Earth's water vapor and get a clearer view. Its mission: to map dust's infrared fingerprints with unparalleled precision, separating the ordinary from the extraordinary. But even SOFIA's keen eye struggles. Dust in the early universe wasn't like today's tidy grains. It was likely messier, hotter, and more unpredictable, forged in the violent deaths of primordial stars. When telescopes catch infrared light from those epochs, they're seeing emission patterns that no lab experiment can fully replicate. The real headache comes from dust temperature degeneracy, a fancy term for a simple headache. Two patches of the CIB might glow identically in infrared, but one could be warm dust in small quantities, while the other is cooler dust in vast clouds. Without knowing which is which, it's impossible to untangle the true source of the light. This confusion has led to wild goose chases, like the time a team thought they'd found evidence of cosmic strings in CIB data, only to realize they'd mapped an unusually spiraling dust cloud in our own galactic backyard. Yet dust isn't just a nuisance, it's also a clue. The very difficulty of filtering it out reveals how extreme the early universe was. Some CIB hotspots might trace back to dust factories, galaxies so crammed with star explosions they spewed ash across entire clusters. Others could hint at entirely new dust physics, where particles behave differently under the extreme pressures of the young cosmos. Missions like JWST are now hunting for these dust-enshrouded monsters, peeling back the veil one wavelength at a time. So while dust might be the CIB's greatest mimic, it's also a silent witness to the universe's most chaotic eras. The key lies in learning its language and knowing when it's lying. One of the most unsettling truths about the cosmic infrared background is how stubbornly unbalanced it appears on the grandest scales. Gaze across the heavens and you'll notice something jarring. The infrared glow isn't spread evenly like butter on cosmic toast. Instead, it clumps and sprawls in lopsided streaks, as if the universe itself tilted during its formative years and let all its infrared light slide to one side. These asymmetries aren't minor wrinkles. They span billions of light years, forming structures so vast they defy the bedrock assumption of cosmology itself, the cosmological principle, which claims the universe should look roughly the same in all directions when viewed at large enough scales. Yet the CIB's uneven whispers suggest we might be staring at something far stranger, a cosmos with a hidden skeleton, a scaffolding of matter so colossal it bends the rules of reality as we know it. The first hints of this imbalance came from Europe's Planck satellite, which meticulously charted the CIB's distribution. Instead of the expected cosmic quilt, a patchwork of evenly distributed light, Planck revealed eerie dipoles, regions where the infrared glow surged in one direction and dimmed in another. Imagine blowing on a dandelion and watching its seeds flee to one side instead of scattering randomly. That's the level of unevenness we're talking about, a tilt so pronounced that chance alone couldn't explain it. Theorists scrambled to reconcile this with the cosmological principle, proposing that perhaps our local galaxy cluster was moving, dragging our observations along with it. But the math refused to cooperate. The CIB's asymmetries were too big, too deep, stretching far beyond any local motion's influence. This is where things get eerie. One leading theory points to superstructures, colossal filaments of galaxies and dark matter woven into the cosmic web, each thread stretching hundreds of millions of light years. Normally, these should balance out when viewed across vast distances. But what if they don't? The CIB's lopsided glow could be the infrared echo of such a megastructure, a gravitational behemoth so immense it pulls matter, and the light it emits into its wake like a cosmic riptide. Picture a river flowing silently through the dark, its current so strong it bends the very fabric of space around it. If such flows exist, they'd rewrite our understanding of how matter clustered in the universe's youth, hinting at primordial density variations far more extreme than our models allow. Even more radical is the idea that these imbalances aren't structures at all, but relics of the universe's birth. Inflation theory posits that the cosmos expanded exponentially in its first fraction of a second, smoothing out wrinkles in space-time. But what if that process wasn't perfectly uniform? Tiny asymmetries in that explosive growth could have snowballed over billions of years, leaving behind infrared, ghost regions where the early universe's expansion stuttered or surged. It's like finding fossilized ripples in what should be a still pond. The most provocative clue comes from cross-referencing the CIB's asymmetries with other cosmic anomalies. The so-called dark flow, a mysterious drift in galaxy clusters seemingly tugged by something beyond the observable universe, aligns suspiciously well with some of the CIB's largest imbalances. Could both be symptoms of the same unseen hand, perhaps a gravitational pull from a neighboring universe or a defect in space-time left over from the Big Bang itself. The data is too sparse to say, but the mere possibility sends shivers down the spine of cosmology. What makes this mystery so profound is its defiance of the very rules we use to make sense of the cosmos. If the universe isn't uniform on the largest scales, then our textbooks and the equations within them are missing something fundamental. The CIB's lopsided glow might be the first crack in a dam, hinting at forces or structures so vast we've yet to grasp their true shape. Until we do, the cosmological principle hangs in the balance, and with it, our confidence in how well we understand the universe's architecture. The cosmic infrared background holds one of its most baffling secrets in the form of an unexpected chill, a mysterious excess of low-energy infrared light that stubbornly refuses to fit any known astrophysical recipe. Think of it like walking into a room warmed by a fireplace, only to discover pockets of cold air that shouldn't exist. This cold excess glows at far infrared wavelengths, where the universe should theoretically be quieter, its light dimmer. Instead, instruments like ESA's Planck satellite have detected a persistent hum in these frigid bands, as if hidden engines are idling in the cosmic dark. What makes this signal so puzzling is its temperature. The excess corresponds to emissions just a few degrees above absolute zero, far colder than typical star-forming regions or even the diffused dust drifting between galaxies. One leading theory points to vast reservoirs of molecular hydrogen, the universe's most primitive gas, lurking in the spaces between early galaxies. These clouds, too diffused to collapse into stars, might have absorbed ambient light and re-radiated it at these frosty wavelengths. Picture an interstellar winter where invisible snowbanks of hydrogen slowly release stored cold light across billions of years. Yet there's a hitch: molecular hydrogen is notoriously difficult to detect directly. Without the heavy elements found in later cosmic eras, these primordial clouds lack the chemical traces astronomers rely on. Planck's data offers only indirect clues, statistical nudges in the CIB's spectral shape that hint at something substantial but unseen. Some models suggest these clouds could stretch for millions of light years, forming a skeletal framework for the cosmic web itself. If true, the cold excess might be the ghostly imprint of the universe's literal dark matter, not the exotic particles we hunt today, but ordinary gas hiding in plain sight. Then there's the wildcard possibility, an entirely new emission mechanism. Certain exotic physics models, including decaying actions or other theoretical particles, predict faint radiation at precisely these wavelengths. Imagine dark matter not as clumps of invisible matter, but as a sea of ultra-low-energy photons constantly leaking into the infrared. It's a tantalizing idea, but the evidence remains circumstantial. When researchers cross-referenced Planck's cold excess with gravitational lensing maps which trace the distribution of all matter, visible or not, the signals didn't fully align. If the excess were truly universal, its fingerprint should appear everywhere. Instead, it flickers unevenly like a faulty wire in the cosmic circuitry. The most provocative twist comes from comparing the cold excess to another cosmic anomaly, the missing baryon problem. Roughly half the ordinary matter predicted by the Big Bang remains unaccounted for, and some theorists speculate these lost atoms might be hiding in diffuse, cold gas clouds, the very structures potentially glowing in the CIB's far infrared tail. It's a cosmic hide-and-seek game where the hiders might finally be betraying their position through this faint thermal whisper. Ultimately, the cold excess forces us to confront how little we know about the universe's quieter corners. While telescopes chase the brilliance of stars and galaxies, this subtle signal reminds us that the darkest, coldest reaches might hold keys to the cosmos's deepest secrets. Until we can peer deeper, perhaps with next-generation far-infrared observatories, this chill in the data will linger, a quiet enigma waiting to be unraveled. If there's one rule astronomers rely on, it's that the universe's grandest structures move at a glacial pace. Stars burn for billions of years, galaxies drift apart over eons. Nothing should flicker on human timescales. Yet the cosmic infrared background seems to break this cardinal rule. Recent studies claim patches of this ancient glow brighten and dim over mere years, as if cosmic ghosts are flipping switches in the dark. If true, this variability would rewrite physics, pointing to objects so unimaginably vast and violent they make supernova look like firecrackers. But the debate raging in astrophysics circles isn't just about what could cause this, it's about whether we're seeing reality at all, or just the echoes of our own instruments playing tricks on us. The controversy began when a team analyzing decade-old Spitzer Space Telescope data noticed something unsettling. Certain regions of the CIB showed subtle fluctuations between observations, not random noise, but statistically significant shifts in brightness. At first, researchers assumed it was calibration errors or interstellar dust passing through Spitzer's field of view, but the signal persisted. Worse, it clustered in ways that defied instrumental explanations, aligning with areas where the CIB already showed anomalous structure. The implications were staggering. Either the universe had unleashed transients brighter than anything in recorded history, or our understanding of infrared astronomy had a gaping hole. Enter the hypernova hypothesis. Picture a star not just dying, but disassembling itself in a cataclysm so extreme it outshines entire galaxies for weeks. Theoretical models suggest these monsters, called superluminous supernova or magnetar-powered hypernova, could exist in the early universe where stars grew to hundreds of solar masses. Their explosions would launch jets of plasma at near light speed, heating surrounding dust to infrared brilliance before fading into oblivion. If enough of these detonated in quick succession within a single primordial galaxy, they might explain the flickering. But here's the catch: even the most extreme hypernova models fall short by orders of magnitude. To visibly alter the CIB's glow, you'd need thousands erupting in sync, a stellar Armageddon with no known natural trigger. That's where the skeptics pounce. Critics argue these variations are artifacts of comparing datasets from different telescopes with unique sensitivities and noise profiles. Spitzer, Herschel, Wise each sees the infrared sky through slightly different eyes, and stitching their observations together risks creating false signals like seams in a patchwork quilt. One team even reanalyzed the original data with stricter error margins and found the fluctuations vanished into statistical noise. The backlash was swift, with some calling it a classic case of seeing patterns in the cosmic static. Yet the mystery refuses to die. New evidence from Japan's Akari satellite added fuel to the fire, detecting similar variability in completely different regions of the CIB. And if instrumental errors were to blame, they'd likely scatter randomly, not cluster around known overdensities in the infrared background. This odd correlation has birthed fringe theories like boson stars collapsing into primordial black holes or dark matter annihilations flaring up in dense pockets of the early universe. These ideas hover at the edge of credibility, but they underscore a brutal truth. If the CIB truly flickers, our playbook for cosmic energetics is missing entire chapters. What makes this debate so electrifying is its stakes. Confirming time variability would mean the universe harbors engines of destruction beyond anything in our current catalog's objects that defy not just observation but imagination. Alternatively, proving it's an illusion would expose critical flaws in how we compare cosmic datasets, forcing a reckoning with the limits of our technology. For now, the jury's out, but next-generation telescopes like SpherX may settle the score by monitoring the CIB in real time. Until then, the question lingers: are we watching the universe's biggest fireworks display, or just the shadow of our own instruments dancing on the wall? The cosmic infrared background might hold the key to one of cosmology's greatest turning points, the moment the universe woke from its dark ages in a blaze of ionizing fury. This is the epoch of reionization, a cosmic dawn when the first stars and galaxies flooded space with enough ultraviolet radiation to strip electrons from every hydrogen atom in existence, transforming the cosmos from a dense fog into the transparent expanse we see today. But here's the puzzle. The CIB's faint glow seems to carry echoes of this upheaval, its patterns hinting at how and what actually powered this universal metamorphosis. For decades, astronomers assumed massive stars were the heroes of this story. These early giants, hundreds of times heavier than our sun, would have burned ferociously before exploding, their UV photons punching holes in the hydrogen fog like sunlight melting frost. The CIB, in this view, should be littered with the infrared aftermath heated dust from galaxies nestled inside these growing ionization bubbles. Yet when scientists modeled this process, the CIB's large-scale structure refused to cooperate. The infrared glow isn't clustered in ways that match simulations of star-driven reionization. Instead, it sprawls in odd filaments and knots, as if something far more exotic helped carve the universe into light. One radical candidate: supermassive black holes in their infancy. Imagine quasars flaring to life not as rare beacons, but as countless embers scattered across the early cosmos. Their X-ray jets would have ionized hydrogen far more efficiently than stars, creating vast, overlapping bubbles that leave a distinct infrared signature. Recent observations from the James Webb Space Telescope lend weight to this idea, revealing distant galaxies with active black holes much earlier than expected. If these monsters were common, their collective fury might explain why the CIB's fluctuations look less like the gentle imprint of stars and more like the jagged scars of something far more violent. But the plot thickens. Some regions of the CIB show infrared excesses with no visible ionizing sources, no galaxies, no quasars, just eerie glowing patches where the universe turned transparent long before it should have. This has led to fringe theories like decaying dark matter particles emitting just enough UV to chip away at the hydrogen fog, or perhaps primordial black holes forged in the Big Bang's first seconds, evaporated in a shower of radiation that jump-started reionization. These ideas hover at the edge of credibility, but the CIB's stubborn mismatches keep them alive. The most tantalizing clue lies in the timing. Reionization wasn't a single event, it unfolded in fits and starts over hundreds of millions of years. By mapping the CIB's spectral distortions, researchers have spotted what might be its earliest stirrings, infrared signals dating to just 200 million years after the Big Bang, long before the first stars were thought to shine. If verified, this would mean the universe's great awakening didn't follow the script we've written for it. Something else lit the fuse, something whose infrared fingerprints we're only now learning to read. What makes this mystery so urgent is its stakes. Reionization didn't just clear the cosmic fog, it set the stage for every galaxy, star, and planet that followed. If the CIB's whispers force us to rewrite that chapter, we might be staring at the origin story of everything we know and the shadow of forces we've yet to name. Trying to isolate the cosmic infrared background is like listening for a whisper at a rock concert, except the instruments playing aren't just loud, they're cosmic. One of the biggest culprits muddying the signal, zodiacal light, the eerie glow of sunlight reflecting off dust grains scattered across our solar system. This interplanetary haze isn't just a nuisance. It's a master of disguise, mimicking the CIB's diffuse infrared shimmer so well that even the most sophisticated algorithms get fooled. Picture astronomers as detectives, sifting through layers of overlapping fingerprints where every suspect wears the same glove. The problem isn't just brightness, it's structure. Zodiacal light isn't uniform. It swirls in delicate bands and knots, tracing the orbits of comets and asteroids that shed dust over millennia. These patterns blend seamlessly into the CIB's own fluctuations, creating false hotspots and voids where none should exist. To complicate things further, our solar system's dust cloud isn't static. As Earth orbits, our perspective shifts, causing the zodiacal light to flicker subtly across seasons. A cosmic strobe effect that can masquerade as variability in the ancient infrared glow. Even missions like COBE and Planck, armed with painstaking dust models, sometimes couldn't tell where the solar system ended and the primordial universe began. Then there's the galactic foreground, a fog of interstellar dust lit up by the Milky Way stars, radiating in the same infrared wavelengths as the CIB. Think of it as trying to photograph distant mountains through a blizzard, where every snowflake glows like a distant peak. Advanced techniques like component separation use statistical tricks to tease these signals apart, treating the sky like a stack of transparencies, each layer a different emitter. But the math hits a wall when the layers aren't just overlapping, they're tangled. Galactic dust emits in complex ways depending on temperature, composition, and even magnetic alignment, creating spectral knots that no algorithm can fully unravel. The breaking point came with an embarrassing revelation. Some of the CIB's most celebrated anomalies turned out to be nothing more than local dust clouds, their infrared echoes misread as whispers from the early universe. One team spent years chasing what they thought was a colossal primordial galaxy cluster, only to realize they'd mapped the faint afterglow of a nearby star-forming region in our own galactic backyard. It's a humbling reminder that space isn't just vast, it's layered, with history written on parchment so thin that every line bleeds into the next. Yet within this chaos lies a perverse opportunity. The very difficulty of isolating the CIB has forced astronomers to invent new ways of seeing. Take limb darkening, a technique borrowed from solar physics, where researchers study how the zodiacal light fades at the edges of Earth's orbit to back-calculate its true brightness. Or cross-correlation, where scientists compare infrared maps with gravitational lensing data to spot regions where the CIB's glow aligns with invisible mass, hinting at signals too consistent to be mere dust. The ultimate irony, these foreground contaminants might hold their own cosmic secrets. Zodiacal dust carries forensic clues about the solar system's violent youth, while galactic cirrus clouds reveal how stars recycle their ashes into new generations. Even as they obscure the CIB, they remind us that the universe's story isn't just written in its oldest light, it's etched into every speck of dust along the way. What makes this mystery so profound isn't just the technical headache, it's the philosophical lesson. The CIB isn't some pristine signal waiting to be uncovered. It's a conversation, a chorus of overlapping voices from every epoch of cosmic history. Separating them isn't just about cleaning the data. It's about learning to listen to the universe in all its messy, magnificent complexity. And sometimes the static isn't noise, it's the sound of everything else singing along. Light isn't just about brightness, it's about direction. And when astronomers detected something bizarre in the cosmic infrared background, subtle hints that its glow wasn't just diffuse but polarized, it sent shockwaves through cosmology. Polarization means light waves are vibrating in a preferred orientation, like ocean waves all rolling east instead of chaotically. For the CIB, this shouldn't happen easily. This ancient light has traveled billions of years, scattered and rescattered by dust and gas, which should have scrambled any primordial order. Yet here we are, with whispers of alignment in the universe's oldest infrared whisper. The first clue came from the Planck satellite's painstaking maps. While most of the CIB's polarization was dismissed as local dust interference, a handful of regions showed stubborn coherence, patches where the infrared light vibrated in eerily consistent directions. At first, researchers blamed spinning dust, tiny grains set spinning by starlight or magnetic fields, emitting polarized radiation as they twirl. It's like expecting a disco ball's reflections to be random, only to find them all pointing northeast. But when models simulated this effect, the predicted polarization was orders of magnitude weaker than what Planck glimpsed. Something else was at work. That's when theorists turned to an electrifying possibility: primordial magnetic fields woven into the fabric of space-time during the Big Bang itself. If these fields existed, they could have stretched across the infant universe, aligning dust grains and electrons like iron filings near a magnet. Over eons, as the cosmos expanded, those seeds might have grown into vast, invisible networks, cosmic power grids imprinting their structure onto the CIB's light. The implications are staggering. Not only would this rewrite our understanding of the universe's first moments, but it could explain how galaxy clusters today are threaded with magnetic fields billions of light years long, far too colossal to have formed by conventional means. Yet skepticism lingers. Detecting weak polarization in something as faint as the CIB is like trying to spot a single blade of grass bending in a hurricane. Critics argue that even subtle instrumental quirks, like the way a telescope's detectors interact with Earth's own magnetic field, could mimic the signal. Others point to galactic dust lanes, interstellar clouds where magnetic fields already align dust grains, potentially contaminating the CIB's pristine signal. But here's the twist: some of the most polarized CIB patches lie between galaxies, in voids where local dust is nearly absent. The boldest proposals venture into uncharted physics. Could this polarization be a fingerprint of cosmic strings, hypothetical spacetime defects left over from the universe's birth, vibrating like guitar strings and warping the light that passes near them? Or perhaps evidence of actions, hypothetical particles that could convert into polarized photons in the presence of magnetic fields? These ideas hover at the edge of science fiction, but the CIB's polarized whispers refuse to fit neatly into any conventional box. What makes this mystery so thrilling is its dual nature. If the polarization is truly primordial, it's a direct line back to the universe's first picoseconds, a snapshot of forces at work before stars or galaxies even existed. But if it's an illusion, a trick of dust or instrumentation, it's a masterclass in how hard it is to listen to the cosmos without hearing our own echoes. Future telescopes like the upcoming Lightbird mission aim to settle the debate with polarization detectors 100 times sharper than Planck's. Until then, the CIB's cryptic alignment remains a riddle written in light's hidden geometry. The James Webb Space Telescope was supposed to bring the universe's first galaxies into focus, not set them on fire. Yet that's exactly what happened when JWST peeled back the cosmic curtains to reveal galaxies so shockingly bright, so impossibly massive, that they've ignited a crisis in cosmology. These aren't just ancient starlights flickering in the void. They're full-blown cosmic beacons blazing with the brilliance of modern galaxies, all crammed into an era when the universe was barely 2% of its current age. The discovery didn't just rewrite galactic evolution, it sent scientists scrambling back to their CIB models, realizing these monstrosities might hold the key to one of infrared astronomy's longest-standing puzzles: why the early universe's glow is so much brighter than it ever should have been. Let's break the absurdity down. JWST high redshift galaxies, objects like Glass Z13 and Sears 93316 shouldn't exist under our current cosmic playbook. They're packing hundreds of billions of stars, some already red and dead. Astronomers speak for mature and burned out, all before the universe celebrated its 500 millionth birthday. For context, that's like finding a fully gray-haired toddler, a biological impossibility that would upend our understanding of human development. These galaxies didn't just form fast, they burned through their fuel reserves with reckless abandon, spewing infrared radiation that would have left an unmistakable fingerprint on the cosmic infrared background. Yet when researchers cross-checked, the math didn't add up. Even if every galaxy JWST found blazed at full throttle, their combined output wouldn't fully explain the CIB's excess glow. Either we're missing something fundamental about how starlight interacts with cosmic dust, or these galaxies are just the tip of a hidden iceberg, one radical solution. Early galaxies weren't just luminous, they were filthy. Picture stellar nurseries drowning in soot, where newborn stars churned out dust at rates 1,000 times higher than modern galaxies. This ash would have absorbed their ultraviolet fury and re-radiated it as infrared, amplifying their contribution to the CIB far beyond their visible light. JWST might be seeing only the brightest cores of these dust-shrouded monsters, while their true infrared footprint, their hidden light, lingers in the background like the afterglow of a fireworks finale. Supporting this, some of these galaxies show spectral signatures of carbon grains and silicates, materials normally forged over generations of star death and rebirth. Their presence so early hints at a universe that didn't just evolve faster than we thought. It industrialized, but here's where the plot twists. If these galaxies are over-contributing to the CIB, they'd leave other breadcrumbs-specific patterns in the infrared fluctuations that telescopes should have spotted. Instead, the CIB's structure remains stubbornly inconsistent with even the most extreme galactic models. This mismatch has birthed a fringe but fascinating alternative. What if the problem isn't the galaxies, but the space between them? Some theorists suggest the early universe was threaded with invisible, dark stars, theoretical objects fueled not by nuclear fusion but by dark matter annihilation. These phantom suns could have burned cold and long, their infrared emissions blending seamlessly into the background without leaving JWST visible traces. Others propose a wilder fix that cosmic expansion didn't unfold as smoothly as we believe. If certain regions of space expanded slower in the past, light from early galaxies would have piled up over time, creating localized infrared hotspots that skew the CIB's average brightness. The most unsettling possibility: we've been misreading the CIB all along. What if its excess glow isn't from galaxies at all, but something beyond the standard model, like decaying actions or primordial black holes evaporating in a shower of infrared photons? JWST discoveries have torn open the envelope of plausible explanations, forcing us to confront how little we truly grasp about the universe's first chapters. Every new observation tightens the knot. The CIB's light demands more energy than known sources can provide, while the brightest candidates JWST finds still fall short. It's a cosmic accounting error with trillion star stakes, and solving it might require ripping up the ledger entirely. For now, these two bright galaxies stand as both clue and red herring flares in the dark that illuminate our ignorance more than our understanding. As JWST peers deeper, each new detection sharpens the paradox, leaving astronomers to wonder: are we staring at the outliers of cosmic history, or the first hints of a universe fundamentally stranger than we dreamed? The cosmic infrared background doesn't just glow, it breathes, pulsing with strange irregularities where the universe's emptiest stretches should be silent. These are the voids, vast deserts of space spanning hundreds of millions of light years, where galaxies are so sparse you could fly for eons without encountering a single star. Yet when astronomers map the CIB's distribution, these cosmic wastelands flicker with infrared light, as if something hidden is stirring in the dark. The paradox is maddening. Voids are defined by their lack of matter, their gravitational pull too weak to cluster dust or stars. So why does the CIB's glow seep into these regions like whispers in a vacuum? One unsettling possibility is that voids aren't empty at all. They're laced with rogue stars, exiled from their home galaxies by ancient collisions or gravitational slingshots. Picture a lone traveler wandering an endless desert, unseen but leaving footprints in the infrared sand. These stellar castaways would be too dim to spot individually, but collectively, their faint heat could imprint on the CIB. The math is tantalizing. Simulations suggest even a sparse population of rogue stars, adrift for billions of years, could explain the infrared excess. But when telescopes like Hubble stare into the voids, they find no trace of them, just yawning blackness. Either these stars are camouflaged by cosmic dust, or they're emitting light in ways we can't yet detect. Then there's the gravitational twist. Einstein's theory dictates that gravity's pull should weaken in voids, their low-density expanse offering little resistance to light's journey. Yet some CIB measurements hint that voids might be bending infrared photons ever so slightly, as if their gravity is stronger than expected. This anomaly has sparked radical theories, like voids within voids, nested structures of invisible matter that warp spacetime like a hall of mirrors. Alternatively, modified gravity models like MAN propose that the rules of attraction change in extreme emptiness, subtly amplifying the pull of what little matter exists. The strangest clue comes from cross-referencing the CIB with cosmic microwave background maps. In some void regions, the CMB's temperature dips slightly, a sign that photons lost energy while traversing these expanses. If voids were truly empty, this shouldn't happen. Yet the CIB's infrared glow in these same areas suggests an energy gain, as if something in the voids is both sapping and radiating light. One explanation: primordial black holes peppered through the voids like invisible anchors, their gravitational wells stealing energy from passing CMB photons while their Hawking radiation leaks infrared heat into the CIB. But perhaps the most haunting idea is that voids aren't anomalies, they're the universe's true default state, and we're the outliers. The CIB's glow in these regions might be a relic of a time before galaxies formed, when matter was spread almost evenly, and the first flickers of infrared light seeped into the cosmos. If so, these silent stretches aren't voids at all, they're windows into the universe's untouched infancy, where the CIB's whispers remain undisturbed by the clatter of stars and galaxies. What makes this mystery so profound is its scale. These voids aren't small, some are so vast they dwarf superclusters. If the CIB's infrared light traces something real within them, whether rogue stars, hidden physics, or echoes of the primordial cosmos, it forces us to rethink not just voids, but the very fabric of space-time. Until we solve the riddle, these cosmic deserts remain the ultimate frontier, where the universe's oldest light meets its most enigmatic emptiness. Fast radio bursts are cosmic enigmas, blinding flashes of energy that outshine entire galaxies for mere milliseconds before vanishing without a trace. But what if these mysterious signals aren't just transient fireworks? What if they leave behind ghostly fingerprints in the cosmic infrared background? Here's the spine-tingling coincidence. Some of the most precise FRB localizations overlap eerily with unexplained CIB hotspots, as if whatever engine powers these bursts also lingers in infrared long after the radio fade. It's like finding a crime scene still warm hours after the suspect fled, evidence of a connection we're only beginning to glimpse. The prime suspect, magnetars, the universe's most volatile dead stars. These city-sized neutron stars pack magnetic fields so intense they could strip atoms apart at 1,000 kilometers away. When they crack under the strain literally as their crusts rupture in starquakes, they unleash energy across the spectrum from gamma rays to radio waves. But here's the twist. Models suggest the aftermath of such eruptions should also superheat surrounding dust, creating infrared echoes detectable for months or even years. Imagine a cosmic blast furnace, where the initial explosion screams in radio while the cooling debris hums in infrared. If magnetars truly drive some FRBs, their lingering heat might stitch these fleeting bursts into the CIB's tapestry, like cosmic breadcrumbs leading back to the scene. Yet the plot thickens when you examine the numbers. While some FRBs do align with CIB excesses, others blaze from regions conspicuously dark in infrared. This inconsistency has birthed a wilder theory. Perhaps only a subset of FRBs, the repeaters that flash multiple times, leave infrared traces, while one-off bursts stem from cataclysms like neutron star collisions that vanish without thermal residue. Supporting this, a handful of repeating FRBs show persistent radio counterparts, hinting at ongoing energy injection that could plausibly heat dust to infrared glow. It's the difference between a single lightning strike and a smoldering wildfire. One leaves scorched earth, the other just a memory of light. The most tantalizing data point comes from FRB 190523, a burst localized to a galaxy 7 billion light-years away. Follow-up observations revealed not just an FRB, but a diffuse infrared haze in its host region far brighter than the galaxy's stars alone could explain. Theorists scrambled. Was this the smoking gun linking FRBs to CIB anomalies? Skeptics countered that the haze might be unrelated star formation, but the infrared excess was too perfectly centered on the FRB's origin to dismiss entirely. Then there's the dark horse candidate, cosmic strings. These hypothetical spacetime defects, if they exist, could theoretically vibrate like plucked violin strings, emitting both FRBs and infrared radiation as they decay. While speculative, the idea gains traction from the sheer improbability of certain FRB-CIB overlaps. Some align too precisely to dismiss as chance, yet defy conventional astrophysical explanations. What makes this mystery so electrifying is its scale. If FRBs and the CIB are truly in dialogue, we might be decoding a new cosmic language, one where millisecond radio screams and billion-year infrared whispers tell two halves of the same story. Future telescopes like the Square Kilometre Array could settle the debate by nailing FRB positions with pinpoint accuracy, letting us scan for infrared counterparts in real time. Until then, these fleeting bursts and their ghostly infrared shadows remain a tantalizing "what if?" a hint that the universe's most explosive moments might echo far longer and far quieter than we ever imagined. There's a cosmic heist underway. Half the universe's ordinary matter has vanished without a trace. These missing baryons, the protons and neutrons that make up everything from stars to human hands, should be out there, but our telescopes catch only whispers of their presence. Now, astronomers are turning to the cosmic infrared background as their most promising lead, speculating that this elusive matter might be hiding in plain sight, woven into the CIB's faint glow like a fingerprint pressed into cosmic dust. The mystery begins with simple accounting. After the Big Bang, the universe was forged with a precise amount of ordinary matter, enough to fill galaxies, stars, and planets. Yet when scientists tally up everything observable today, from glowing gas to distant quasars, nearly 50% is unaccounted for, the leading theory. These baryons aren't truly missing, they're just invisible, strung through intergalactic space in a diffuse web of warm, hot gas too tenuous to detect with conventional telescopes. Picture a ghostly ocean between galaxies, its currents too faint to see but vast enough to swallow all the missing atoms whole. That's where the CIB comes in. If this intergalactic gas is heated even slightly by shock waves from colliding galaxy clusters or energy from active black holes, it could emit a faint infrared signature, blending seamlessly into the cosmic infrared background's haze. The math is tantalizing. Simulations show that even gas at a few 100,000 degrees, a lukewarm bath by cosmic standards, would radiate at wavelengths just long enough to mimic the CIB's spectral bumps. It's like hearing static on a radio and realizing too late that buried in the noise was a voice all along. The hunt for these baryonic ghosts hinges on a technique called cross-correlation. By overlaying CIB maps with gravitational lensing surveys, which trace all matter, visible or not, researchers have spotted infrared excesses aligned with the cosmic web's predicted filaments. These aren't the blazing trails of galaxies, but faint infrared smudges where the maps say invisible gas should lurk. One study using data from the Planck satellite found tentative matches between CIB fluctuations and the projected locations of these warm, hot filaments, as if the universe's missing matter was finally casting a shadow. Yet the evidence remains frustratingly circumstantial. The biggest hurdle, separating this hypothetical baryonic glow from the CIB's other contributors, dusty galaxies, primordial stars, even dark matter's potential echoes. Some models suggest the combined infrared output of all known sources still leaves room for the warm, hot gas to contribute, but proving it requires instruments sensitive enough to tease apart overlapping signals. Enter upcoming missions like the European Space Agency's Athena X-ray Observatory, designed to directly detect the faint X-ray emissions this gas should also produce. If its findings align with CIB anomalies, the case for baryons hiding in the infrared could solidify overnight. The stakes couldn't be higher. Solving the missing baryon problem isn't just about balancing the cosmic books, it's about understanding how matter flows between galaxies, fueling star formation and shaping the universe's large-scale structure. If the CIB is indeed a graveyard of lost atoms, its glow might be more than ancient light. It could be the signpost to everything we've overlooked. Until then, the hunt continues, with astronomers sifting through infrared static for the faintest echoes of the universe's hidden bones. Zoom in close enough on the cosmic infrared background, and the universe's grand tapestry unravels into something far stranger, a labyrinth of microscopic knots and threads, where infrared light clumps in ways that defy every dark matter simulation we've ever run. This isn't just noise, it's structure at the smallest scales imaginable, patterns so intricate they'd require a cosmic microscope to fully decipher. If the large-scale CFB is a hazy panorama of the early universe, these fine-grained fluctuations are its hidden brushstrokes, each one whispering secrets about how matter, both seen and unseen, first wove itself into the cosmic web. For decades, cosmologists assumed dark matter behaved predictably, clustering under gravity's pull into halos that served as scaffolding for galaxies. Supercomputers churned out simulations where this invisible skeleton grew steadily, its tendrils branching like frost on a windowpane. Yet when astronomers compared these models to the CFB's small-scale flickering, the mismatch was glaring. Instead of smooth gradients, the infrared background bristled with sharp peaks and troughs, as if someone had scattered handfuls of glowing sand across the sky. Some regions showed excess clustering 100 times denser than simulations predicted, while others gaped with unexplained voids. It's like expecting the quiet hum of a forest at night, only to hear bursts of static erupting from unseen creatures. One leading theory points to ultra-compact minihalos, hypothetical nuggets of dark matter so dense they'd act like cosmic magnets, pulling ordinary matter into tight, bright knots. These objects, if they exist, would have formed in the universe's first seconds, their gravitational grip amplifying the CFB's small-scale structure far beyond standard predictions. Supporting this, certain anomalies in the CIB's power spectrum. The mathematical fingerprint of its fluctuations align eerily with what ultra-compact minihalos should produce. Yet skeptics counter that no other evidence for these objects exists, leaving them stranded in theoretical limbo. Then there's the explosive alternative. Perhaps dark matter isn't as cold as we thought. The prevailing cold dark matter model assumes particles move sluggishly, clumping easily into vast halos. But if dark matter had even a whisper of heat, if it jostled slightly in the early universe, it could have resisted clustering at the smallest scales, leaving gaps in the infrared tapestry. This warm dark matter scenario would imprint a distinct cutoff in the CIB's fine structure, a signature some researchers claim to detect in the data. Yet when telescopes hunt for this cutoff, the results flirt with contradiction, too fuzzy to confirm or deny. The most tantalizing clue lies in cross-referencing the CIB's small-scale patterns with gravitational lensing maps. Where the infrared glow clumps unexpectedly, space-time often warps more sharply, as if unseen masses lurk there. But here's the twist: these lenses don't always align with known galaxies or clusters. Instead, they trace ghostly arcs of gravity, hinting at dark matter halos too sparse to host stars yet dense enough to bend light and sculpt the CIB's minute flickering. Some theorists speculate these could be failed galaxies, regions where dark matter coalesced but ordinary matter never ignited. Others wonder if we're seeing the fingerprints of primordial black holes, their compact gravity punching tiny dimples into the infrared sky. What makes this mystery so revolutionary isn't just the anomalies, it's the stakes. If dark matter clumps differently than our simulations, entire chapters of cosmic history might need rewriting. Galaxy formation, the growth of supermassive black holes, even the universe's expansion rate could be tangled up in this enigma. The CFB's small-scale structure isn't just a puzzle, it's a stress test for cosmology itself, probing whether our theories can withstand the universe's messy, microscopic reality. Until we crack its code, these infrared whispers remain a haunting reminder. The cosmos reserves its most surprising secrets for those who look closest. Buried within the cosmic infrared background's diffuse glow might lie the universe's most sacred relic, the first light to pierce the cosmic dark ages. This isn't just ancient starlight. It's the infrared echo of the moment the universe switched on, when the first stars and galaxies ignited, ending billions of years of utter blackness. But here's the catch: isolating this cosmic dawn signal is like trying to hear a single note in a symphony played at the edge of the observable universe. The CIB's haze is a palimpsest, layer upon layer of light from countless epochs, all blurred together into a single whisper. Yet subtle anomalies in its spectral fingerprints suggest something extraordinary, a primordial imprint waiting to be decoded. The hunt hinges on a telltale signature, a spectral bump at around 1.6 micrometers, a wavelength theorized to mark the radiation from the universe's very first stars. These weren't just any stars, they were behemoths, hundreds of times more massive than our Sun, burning ferociously and dying young in supernova so violent they seeded the cosmos with heavy elements. Their ultraviolet light, stretched by cosmic expansion into the infrared, should leave a faint but distinct ripple in the CIB's spectrum. Think of it like carbon dating the universe's infancy, but instead of radioactive decay, we're measuring the afterglow of the first stellar fires. But controversy simmers. Critics argue this signature could easily be masqueraded by later galactic pollution, dust from dying stars, or the collective glow of black holes. The real smoking gun would be a specific pattern in the CIB's fluctuations, a statistical echo of how those first stars clustered in the primordial darkness. Simulations suggest these pioneers didn't light up randomly. They ignited in tight-knit groups, their collective radiation carving ionized bubbles into the hydrogen fog. If that structure survived in the CIB's large-scale patterns, it would be the ultimate confirmation. Enter SPHEREX, NASA upcoming infrared spectro-imager, poised to launch as early as 2025. Unlike its predecessors, which scanned broad swaths of the infrared sky, SPHEREX will dissect the CIB's light across 96 distinct wavelength bands, hunting for the cosmic dawn's spectral fingerprint with unprecedented precision. It's the difference between hearing a roar and isolating the individual voices in a crowd. By cross-referencing these spectral slices with maps of the cosmic microwave background, SPHEREX could trace how the first star's energy propagated through the early universe, painting a dynamic portrait of cosmic awakening. Yet the challenges are staggering. The cosmic dawn signal, if it exists, is buried under eons of infrared interference, dust from modern galaxies, emissions from interstellar molecules, even the thermal whispers of our own solar system's debris. Filtering out this noise requires algorithms sharp enough to separate the universe's oldest light from the static of its later history. One innovative approach involves tomography, stacking CIB data at different redshifts to reconstruct a 3D map of the early universe's ionization fronts. It's akin to peeling an onion layer by layer until only the primordial glow remains. The stakes couldn't be higher. If SPHEREX or future observatories like the European Space Agency's Ariel mission succeed, we'll glimpse the universe's very first structures, not just stars, but the gravitational wells of dark matter that funneled them into existence. We might finally witness the moment gravity's quiet patience gave way to light's explosive dawn. And if they find nothing, that absence would be equally revolutionary, forcing us to rewrite the timeline of cosmic evolution or consider radical alternatives like dark stars, powered not by fusion but by annihilating dark matter, their infrared signatures forever lost in the noise. Either way, the CIB's cosmic dawn mystery is more than a technical challenge. It's a philosophical reckoning. We're not just searching for light, we're chasing the moment the universe became aware of itself, when chaotic hydrogen first kindled into something that could, billions of years later, wonder how it all began. And hidden in that infrared fog, just beyond our grasp, might be the answer. There's a shadowy candidate lurking in the equations of particle physics, one that might explain the cosmic infrared background's strangest glimmers while cracking one of cosmology's toughest cases. Meet actions, hypothetical particles so light they barely interact with matter, yet they might be weaving through the cosmos in uncountable trillions, leaving behind infrared whispers as their only calling card. Theorists first dreamed up actions to solve an esoteric puzzle in quantum physics, but their potential stretches far beyond. They could be the elusive dark matter we've hunted for decades, and the hidden engine behind the CIB's most baffling signals. Picture this, actions aren't just passive cosmic spectators. In the presence of strong magnetic fields, like those around galaxies or threading the voids of space, they can undergo a bizarre metamorphosis, transforming into photons of infrared light. It's as if the universe's invisible scaffolding occasionally flickers into visibility, like a blacklight revealing hidden ink. These converted photons wouldn't blaze like starlight. They'd seep into the CIB's diffuse glow, subtly altering its spectrum in ways that ordinary astrophysics can't replicate. The smoking gun. Certain quirks in the CIB's polarization patterns align eerily with what action models predict, specific twists in the light's orientation that dust or stars can't explain. But here's where it gets wild. If actions are real and converting en masse, they'd solve two cosmic mysteries with one stroke. First, they'd account for the missing mass we call dark matter, invisible yet shaping galaxies with their gravity. Second, their infrared decay products could plug the gaps in the CIB's energy budget, explaining why some regions glow brighter than known sources allow. Imagine killing two birds with one stone, except the birds are galactic-scale enigmas, and the stone is a particle 1 billion times lighter than an electron. Critics aren't sold, of course. The CIB's anomalies could still stem from mundane astrophysics, superheated dust, or overlooked galaxies, and action detection remains frustratingly elusive. Experiments like ADMS hunt for actions in lab-bound magnetic chambers, but the particles' ghostly nature makes them nearly impossible to trap. Yet the CIB offers something labs can't: a natural, universe-sized detector. By scouring its infrared maps for the unique spectral bumps and polarization signatures actions would imprint, astronomers might spot what ground-based experiments miss. The boldest hope lies in the CIB's most perplexing voids, regions where the infrared glow persists despite a near-total absence of conventional matter. If actions truly permeate space, these cosmic deserts could be where they shine brightest, converting freely in the undisturbed magnetic fields between galaxies. Future telescopes like NASA's upcoming SPHEREX mission will dissect the CIB's light with surgical precision, hunting for these telltale voids turned beacons. If they find even a single patch of sky where the infrared excess aligns perfectly with action predictions, it could rewrite particle physics overnight. What makes this possibility so electrifying isn't just the science, it's the sheer audacity of the idea. The CIB, long treated as a fossil of stars and dust, might be alive with the tremors of particles we've yet to confirm, their faint infrared size a language we're only beginning to decode. Whether actions hold the key or not, their potential link to the CIB reminds us that the universe's greatest mysteries often hide in the spaces between what we see and what we know must be there. At the heart of our galaxy, where Sagittarius looms like a silent titan, the cosmic infrared background does something unexpected. It brightens. This isn't just a subtle uptick, it's a glaring anomaly, a hotspot in the infrared haze that defies straightforward explanations. Normally, we'd chalk this up to the frenetic star formation near the galactic center, where molecular clouds collapse into stellar nurseries at a dizzying pace. But here's the twist: the CIB's enhancement here is too intense, too clustered, as if something invisible is amplifying the glow beyond what stars alone could produce. One leading theory points to the obvious culprit: the galactic center's extreme stellar density. Within a few light years of Sagittarius A, stars are packed so tightly they're practically shoulder to shoulder, their collective radiation heating dust to infrared brilliance. Telescopes like Spitzer and Herschel have catalogued thousands of young, massive stars here, each blazing with the energy of millions of suns. Their combined output should indeed light up the CIB like a cosmic bonfire. Yet when astronomers tally the numbers, there's a mismatch. The infrared excess is brighter and more concentrated than the known stellar population can account for, as if hidden furnaces are stoking the flames. That's where the shadowy alternative comes in: dark matter. The galactic center is thought to harbor a dense spike of this elusive substance, a gravitational well so deep it could trap dark particles in a swirling, invisible maelstrom. If dark matter isn't completely inert, if particles can annihilate or decay, this region would be ground zero for such activity, releasing energy that might seep into the infrared. Picture a silent fireworks show where dark matter's self-destruction lights up the sky in wavelengths only our most sensitive telescopes can see. Some models even suggest this process could explain the CRB's peculiar spectral bumps near Sagittarius A, subtle kinks that align with predicted dark matter signatures. But skeptics aren't ready to jump to exotic conclusions. They argue the anomaly might stem from something more mundane yet equally fascinating, a population of obscured protostars hidden behind thick veils of dust. These fledgling stars, still swaddled in their birth cocoons, would emit copious infrared light while remaining nearly invisible in optical surveys. Supporting this, ALMA-millimeter wave scans have glimpsed dense knots of gas and dust in the region, each potentially cradling a stellar newborn. Yet even these detections don't fully bridge the gap, leaving room for more radical ideas. The most tantalizing clue comes from gamma rays. Fermi telescope maps show an excess of high-energy photons emanating from the galactic center, a signal that also aligns suspiciously with dark matter predictions. Could the CIB's infrared glow and Fermi's gamma rays be two sides of the same coin, evidence of dark particles meeting their end and releasing energy across the spectrum? It's a seductive narrative, but correlation isn't proof. What makes this mystery so gripping is its implications. If the CIB's enhancement traces dark matter, it would offer our first tangible glimpse of this shadowy substance's behavior in nature's most extreme laboratory. If it's just hidden stars, we're still learning how the universe's busiest stellar factories operate behind the scenes. Either way, the galactic center's infrared whisper is a reminder. Even in our own backyard, the cosmos keeps its deepest secrets close. The cosmic infrared background holds one of its most perplexing boundaries at redshift 20, a frontier beyond which its signal seemingly vanishes. This isn't just a gradual fade into noise, it's an abrupt drop-off, as if the universe itself flipped a switch and silenced the infrared echoes of its infancy. The implications are staggering. Either star formation hit a hard wall in the universe's first 200 million years, or we're staring at the limits of our own technological gaze, a cosmic horizon we can't yet pierce. Redshift 20 marks an epoch so early that the cosmos was barely recognizable. Hydrogen atoms had only recently formed from the cooling plasma of the Big Bang, and the first dark matter halos were just beginning to pull matter into their gravitational embrace. Conventional models suggest this was too soon for stars, let alone the dust they'd heat to infrared glow, to exist in meaningful numbers. Yet the CIB's sudden silence here raises uncomfortable questions. If the cutoff is real, it implies the universe's first lights flickered on later than our theories predict, leaving a gap in time where even the most extreme galaxies dared not shine. But skepticism lingers. Current telescopes, for all their power, operate at the edge of detectability when probing these redshifts. The James Webb Space Telescope, humanity's most sensitive infrared eye, can barely glimpse galaxies at redshift 15, let alone 20. The CIB's signal at these distances would be stretched into far infrared wavelengths, where Earth's atmosphere and even space-based instruments struggle to gather enough photons. It's like trying to spot a candle through a blizzard. The light might be there, but the storm swallows it whole. Then there's the dust dilemma. Even if stars did ignite before redshift 20, their surrounding dust, the very material that reprocesses starlight into the CIB's glow, might not have had time to form. Heavy elements like carbon and silicon, essential for dust grains, required generations of stellar deaths to seed the cosmos. Without them, early starlight would escape unchanged into ultraviolet, leaving no infrared footprint for us to detect. This creates a perverse scenario. The universe's first stars could blaze unseen, their light lost to the void because the ashes of their ancestors hadn't yet littered the skies. The most tantalizing alternative, the CIB's redshift cutoff, isn't a boundary of physics but of perspective. Some theorists suggest that beyond redshift 20, the universe was so dense that infrared photons couldn't escape their birthplaces without being absorbed and re-emitted countless times. The CIB's light from these eras wouldn't vanish, it would smear into uniformity, blending with the cosmic microwave background like ink dissolving in water. If true, this would mean we're not seeing an absence but a transformation. The moment the universe's opacity reshaped its own archival light, future observatories like the Origins Space Telescope or the Laser Interferometer Space Antenna could settle the debate, probing these redshifts with unprecedented sensitivity. Until then, the CIB's silent frontier remains either a clue to cosmic timing or a mirror reflecting our own limitations. Either way, it's a reminder that some of the universe's loudest mysteries speak in the quietest of absences. Could the violent mergers of black holes leave more than gravitational tremors in their wake? When LIGO first detected ripples in spacetime from colliding black holes, it opened a new window on the cosmos, one where these invisible monsters finally betrayed their existence through gravity's own language. But here's the eerie possibility. Some of these cataclysms might also cast shadows in the cosmic infrared background, their mergers unfolding in environments so thick with dust that the heat of their violence lingers long after spacetime settles. Think of it like hearing thunder in a storm but seeing no lightning, then realizing the flash was there all along, just smothered by fog. Black hole binaries born in dense galactic nurseries, where dust and gas swarm like cosmic fireflies, could heat their surroundings to infrared brilliance during their death spirals. As they circle closer, their gravitational energy doesn't just ripple outward as waves, it could also shred nearby matter, creating shock waves that superheat dust to thousands of degrees. The result, a transient infrared glow, faint but detectable, that flickers in sync with LIGO gravitational chirps. The math is tantalizing. Simulations of merging supermassive black holes, those lurking at galactic centers, predict exactly this kind of infrared flaring as they stir up debris clouds. While LIGO stellar mass binaries are smaller, the principle might still apply if they're embedded in similar dusty environments. Imagine two black holes dancing in a nebulous heart, their final orbits whipping up particle storms that shine briefly in infrared before vanishing into the void. Yet the evidence remains maddeningly sparse. Of the dozens of black hole mergers LIGO has spotted, none have definitive infrared counterparts. But here's the twist: that absence might be a clue in itself. Most detected mergers involve black holes too clean, too devoid of surrounding matter, to leave an infrared echo. This suggests they formed in dry environments like sparse galactic halos where gas and dust were stripped away eons ago. It's the mergers we haven't seen that could be the smoking guns, black holes spiraling in star-forming regions or active galactic nuclei, their dusty shrouds absorbing and re-radiating the collision's energy into the CIB's haze. The hunt now turns to statistical whispers. Instead of chasing individual mergers, astronomers are cross-referencing LIGO event maps with CIB fluctuation catalogs, searching for regions where gravitational waves and infrared excesses overlap more often than chance allows. Early results tease something provocative. Certain patches of the CIB flicker slightly brighter in directions where LIGO mergers cluster, as if the universe is highlighting its own hidden patterns. The implications stretch beyond astrophysics. If dusty mergers imprint on the CIB, they could reveal a population of black holes currently invisible to us, ones born in the cosmic equivalent of a sandstorm, their gravitational waves muffled by the very debris that makes them glow. It's a reminder that the loudest events in the universe might also be the ones hiding in plain sight, their full stories written not just in spacetime's tremors, but in the slow, patient light of ancient dust. Every glow fades eventually, even the cosmic infrared background, that ancient whisper of light spanning the cosmos. Right now, it lingers as a ghostly archive of the universe's wild youth, but its days are numbered. As space stretches relentlessly, the CIB's signal is being pulled thinner, dimmer, more diffuse, like a photograph left out in the rain, its details slowly dissolving into noise. And here's the chilling reality. If we don't decode its secrets soon, they might vanish beyond our reach forever. The math is merciless. The CIB's light has already traveled for billions of years, its wavelengths stretched by cosmic expansion from visible or ultraviolet into the infrared. But the universe isn't just expanding, it's accelerating, driven by dark energy's mysterious push. Over time, this acceleration will redshift the CIB's photons even further, tugging them into millimeter waves, then radio frequencies, until they bleed into the cold silence of the cosmic microwave background. Imagine trying to read a letter where the ink keeps fading. Eventually, even our most sensitive instruments won't distinguish the writing from the page. Current estimates suggest we have perhaps another billion years before the CIB becomes indistinguishable from the CMB's uniform haze. That might sound like a generous deadline until you realize how much we still don't understand. Half the CIB's fluctuations lack clear sources, its spectral kinks defy known physics, and its potential ties to dark matter or primordial particles remain unproven. It's like watching a library burn while we've only read the titles of a few books. But the urgency isn't just about losing data, it's about missing our only window into the universe's most formative era. The CIB captures a specific golden age, after the cosmic dark ages but before modern galaxies fully took shape. Once its signal fuses with the CMB, that epoch's unique fingerprint will blur into oblivion, erasing clues about how stars, black holes, and dark matter conspired to build the cosmos we know. The race is already on. Next-generation telescopes like SPHEREX and the European Space Agency's Ariel mission are fine-tuning their instruments to dissect the CIB's fading light with unprecedented precision. Meanwhile, theorists are scrambling to prioritize which puzzles to tackle first. Should we focus on mapping the CIB's ties to reionization or chase its possible action signatures? Every observation now is a salvage operation, a desperate bid to preserve cosmic history before it slips into the dark. Yet there's a poetic irony here. The CIB's eventual fading mirrors the very processes it records: the dimming of primordial stars, the cooling of ancient dust, the slow dissolution of structure into entropy. In a way, its disappearance will be the ultimate testament to the universe's impermanence, a final echo of all that once blazed bright and now exists only as whispers in the data. Our task isn't just to study the CIB, it's to listen closely while its voice can still be heard. From the eerie uniformity of its glow to the ghostly whispers of potential dark matter decay, the cosmic infrared background has taken us on a journey through 25 of the universe's most tantalizing secrets. We've seen how its flickering patches defy predictions, how its spectral anomalies hint at physics beyond our understanding, and how its faint polarizations might trace back to the universe's very first magnetic fields. Each mystery peels back another layer of cosmic history, whether it's the vanishing galaxies that should exist but don't, the infrared echoes of black hole mergers we can't yet see, or the chilling possibility that actions are hiding in its diffuse light. What makes these puzzles so extraordinary isn't just their complexity, it's what solving them could mean for our understanding of everything. Crack the CIB's code, and we might finally grasp dark matter's true nature, rewrite the timeline of cosmic dawn, or even uncover evidence of parallel universes tugging at our own. This isn't just astronomy, it's detective work on the grandest scale, where every infrared photon is a clue waiting to be deciphered. But here's the thrilling part: this story isn't finished. New telescopes like SPHEREX and Ariel are gearing up to probe the CIB with unprecedented precision, while theorists are crafting ever bolder models to explain its riddles. One day, these mysteries won't be mysteries at all, they'll be chapters in a new cosmic narrative, one we're writing right now. So tell us which of these 25 enigmas fascinates you most. Is it the CIB's eerie link to fast radio bursts, or the way its glow flickers where nothing should move? Drop your favorite in the comments below, and don't forget to subscribe for more deep dives into the universe's greatest unsolved puzzles. The next revelation could be just one observation away, and you won't want to miss it.